now it's a second lecture by John, and he will do more surgery.
No, we're almost done with surgery now. So let me just briefly recap what we did yesterday. So we established the fact that to compute the partition function on a three-manifold cosine theory, you could, in principle, cut it into two pieces, each of which is a three-manifold with boundary that's called sigma. And then the part integral will assign a Hilbert space to this two-dimensional surface H sub sigma, and it also will assign two vectors psi m1 and psi m2 to the two halves. And if the gluing is such that I'm using a diffeomorphism to glue the left half to the right half, then this diffeomorphism will naturally act on the Hilbert space, and in the end, the partition function is just nothing. Just this matrix element. So that's basically what we did last time. And and we have already.
Sorry, why is diffeomorphism?
Right. Okay. So I'm using phi to. That's diffeomorphism of sigma. So and we have seen that. Basically, through doing surgeries along links, we can reach from S3 to any three manifolds, which means we just need to figure out what is the Hilbert space that we assign to a torus, and how to do what is the mapping class, how is the mapping class group acting on this Hilbert space. And for this, we would have to do some real work. Quantization on torus, and before that I have to tell you a little bit about geometric quantization. So, the starting data will be a manifold, a Kähler manifold, where omega, the Kähler form, is in the integral class. So the first step is a pre-quantization. And what we're going to do is that for any function, we want to, for any function, there is two functions. We can define a Poisson bracket, which we just use the inverse of this omega. And then we want to quantize it such that we want to assign an operator. Well, I guess we should go to. So Poisson bracket goes to commutators. That's what we call the pre-quantization. And then pre-quantization has a canonical procedure. The procedure is that we look for a complex line bundle whose first Chern class is omega, which always exists because this condition. And then the operator f hat that we assign to the function f will be, it acts on the space of sections of on this line bundle, and then the definition will be f hat. One more definition. Let me call x sub f as the Hamiltonian vector field generated by f. Vector field generated. Okay. Now, the operator that I assign to the function f will be defined as follows. Minus I x. Where this guy is the covariant derivative. Of course, since we assume that the first Chern class is equal to omega, we naturally have this So to explain this operator, naturally this covariant derivative acts on a space of sections, while this guy just acts by multiplication. And it's quite easy to check using this relation that indeed we have is equal to, okay, which means this is the step of pre-quantization. Now to actually quantize, what we need to do is to choose a polarization. Namely, you have to tell me who is the momentum, who is the coordinate. And my wave function is supposed to only depend on the coordinates, not the momentum. And in this case, we'll have to use this guy. So let me call it, so the wave functions are the holomorphic sections. Are the holomorphic, namely as such that d bar s equal to 0. This roughly says that I'm choosing my, if I choose the coordinates of this manifold to be z and z bar, then that means I'm using z as my coordinate and z bar as my momentum. And then this condition roughly says that the wave function only is a function of z only, not z bar. Okay, so actually, this is all I know about geometric quantization, so I've just told you everything. And now let's do an example. So any questions about this procedure?
But usually one takes a real polarization.
Right, but yeah, actually in the next example, I will first start from the real polarization and then convert it into the complex polarization, and then show you that you could have guessed the answer from the beginning. So, let me do an example. Well, this example will be useful because, well, it's a torus, so let me complex structure tau, and this is 1. And then omega is k is an integer, dx, dy, and x, y are in 0, 1. And if I define the complex variable as x plus tau y, where tau is equal to tau 1 plus I tau 2, of course this guy will have to be greater than 0. If I define z as this, then omega can also be written as minus I k tau 2 dz bar. Okay. So let's first choose a real polarization. And well, before we even set out doing it, we already know that we're supposed to find k states because the integral of omega in this space is equal to k, which means since this is roughly speaking the pixel. Well, you cut this phase space into pixels, and each pixel is roughly of this size. So now let's first, okay, real. So let me just x is here, y is here. Let me choose x as my momentum. This is quite unfortunate. I should have chosen y, but it's too late. Momentum. Now, x being the momentum of y, since y is defined periodically, because it's periodical, which means x has to be discrete since it's a momentum, so its value will be integer divided by k. Okay, I think this is quite clear. But on the other hand, x itself is defined periodically, which means not all of these are different. I need to mod out integers. Okay, and indeed, so the non-equivalent values of x will be 0, 1 over k, da, 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 da. So I exactly find k states. So that's well, that's expected. So we can write the wave function in the momentum basis first. Well, that's quite simple. there's got one label which labels the momentum. It's just going to be delta functions. So if you first just ignore this sum and ignore this n, then that means you have a delta function support. X is supported on these values, and then by summing over m, basically what I'm doing is I'm modeling out this z. Okay, and now this guy can be written slightly differently as so what I'm using is the following relation. So this is the relation I'm using. So I'm just writing this delta, this sort of periodic delta function into a sum of a bunch of exponentials. Okay. So this is so much I can say about the real polarization. Now, complex polarization. So according to what I said there, we're supposed to find a complex line bundle whose first Chern class is this guy. And actually that's quite easy because for line bundles there is this formula that if you choose a Hermitian matrix H, then C1 is just E bar log of H. Okay, so and then of course H has this Kähler-Gauge transformation. You can multiply it by lambda and lambda bar, where lambda and lambda bar holomorphic and anti-holomorphic. This is not going to change the class. So why don't I just choose the first thing that comes to my mind? Let me choose H to be E to the up to a few factors. This is gonna This is gonna reproduce. Where is it? This guy. Yeah. Okay. So what? Yeah, it's pretty easy to check. Now, having found the metric, we just let's say okay. Then the sections of this line bundle will satisfy this condition. So S star times.
So, what did you write? G equals the bar.
C1, sorry.
Oh, C1.
Well,
yeah,
it's not C1 in just Tolman, correct?
Yeah, right. Omega, but
Just
omega
omega.
is C1. Omega is C1. But up to I.
Right.
Right.
The class of omega.
These sort of things that. Okay. But I guess you understand this. So the sections of this line bundle will be such that this guy is doubly periodic. Oh well, it's doubly periodic. And in fact, you could have just guessed that, while looking at this form, S will be something like a theta function. But instead of guessing it, let's just convert this wave function, into the yeah. Okay. So how do we convert? Now we have two polarizations. One, two sets of variables x and y. Z and Z bar. And then there should be a canonical transformation that takes you from here to here, right?
Can I ask a question? The symbol S here, what does when you write S star H, what does that mean?
S is a section of the line bundle. H is the Hermitian metric. So this is just the length of the section.
So S is a...
sorry, S is the section of the line bundle.
It's a bracket S with S bar, just in a scalar product.
Oh, so it's X the other way.
So,
Yeah.
Oh.
so we integrate that. That is equal to what?
Sorry?
What do you do with that? You integrate it. Well, there's no equation.
Oh, well, I didn't want to write that this is double aperiodic. It's a long word. So, okay. Double aperiodic.
So that's going to be your
It's
wave function.
no. Well, I'm trying to figure out what it is.
It's,
Yeah,
it's,
perhaps
a,
I
it's, a,
have-
no, it's a
perhaps
normal
I have
wave
lost the
function,
logic
right?
there.
It's a norm. It's a
Yes, the normal.
Can you repeat your logic here?
So what I'm saying is that the metric you can guess because what you want is the metric. By using this form, you can reproduce this guy. You could guess that one.
Sure.
And then now we try to find what are the sections, right?
Mm-hmm.
The sections will be somewhat double aperiodic. I mean, because this guy has to be well defined on the torus.
No, wait, when you
But-
said what are the
Alessandro,
sections, so you mean
wave functions, whatever you want, but it should satisfy conditions that psi with psi bar should be normal double periodic things. Right?
I'm just asking if that is the wave function.
Yeah, S will be the wave function because if S is holomorphic, then and then if this is well defined.
What is the role played by that guy in the whole discussion here? We have that function, it is doubly periodic. Then
No, okay. What I'm trying to say is that by looking at the form of this metric, and then the fact that this is double periodic, you could have guessed that S will be some sort of theta function. That's what I'm trying to say. I could have deleted it and just go ahead and do that.
I just didn't know this part, so I still don't understand. So
Okay.
just trying to
But anyway, we'll see
say,
it in a minute.
can deal with.
So the canonical transformation, well, it's generated by a function which is supposed to depend on only one of the old variable and one of the new variable. In this case, I would choose it to depend on x, which is old variable, and z, the new variable. And it can be worked out as follows. F is equal to minus I k I L. So it, roughly speaking, satisfies, well, it satisfies this relation. Which is what you would have expected from a canonical transformation. Not clear? Okay, now, do I need to explain?
Couldn't you just say that that's needed to be a section of that line bundle and so just giving us the answer?
Yeah, the answer will show up in a minute.
No, I mean, we know what the sections are of this line bundle on a torus. That's what you're doing. You're rederiving this. Okay, good.
Yeah, okay. So do I need to explain about the fact about this canonical transformation? So you take a generating function depending on one old variable and one new variable, and then roughly roughly speaking, f dx should be the y, and df over the z should be z bar. That's the definition of the, I don't know, I think the first canonical transformation of the first type, I think. Anyway, so if you rewrite this condition into this, all right. So what you do next is that you just, by applying this this guy to the wave function, which is here, and integrate of x, what you will find is following. What you find is all right. Some function. find is this, and it looks awful terrible. But after applying a few Poisson resummations and some jiggling, will turn out to be like this. Okay, so this theta function, well, this is actually, well, this is the theta function. Let me write down the expression later, but I just want to comment that the reason I said it was a bit unfortunate in the beginning that I chose x to be the momentum is that everything comes out lopsided. You know, I could have chosen y, then these will become tau and instead of, you know, but theta is, well, this is just necessary. You can apply the non-transformation property of theta and get the correct answer. Now, this part, actually, I'm just going to combine this with the metric because this is holomorphic, right? So I said I can transform well, the metric with any stuff like that, and I'm not going to change anything. So the new metric is going to be just in fact, this is the standard metric for theta functions. Well, I mean, I sort of deliberately chose the non-standard one, and in the end I still get the correct one. But anyway, so what are the theta function here? Theta function is equal to theta p k. That's the theta function well, with two levels. In fact, for Chern-Simons theory, this guy is the Weyl theta function related to SU2. But yeah, we'll get this later again. Okay, so this is a short example, and any questions about that? All right, so let's do Chern-Simons theory now. Again, before we plunge in, let's
just one question. I mean, you got, I mean, you use this polarization for fixed complex structure, right, on the top.
Right, yes.
A priori, if you I mean, if you change complex structure, it will be another polarization.
Right, actually, this term will turn out to be the, okay. Yeah, right, actually, when you do things correctly, you will get an extra term, which is e to the tau 2, something like that, and then that's the how should I say? That's the metric. Well, let me comment on this later. So I guess so. Let me just comment on his question actually. So he's saying that with different complex structure, the Hilbert space is slightly different, but there's a way of identifying them for different taus, and yeah. Okay, so what are we to expect from quantizing Chern-Simons theory? So we have again torus, and we know that pi1 of torus is abelian, and we also know that and we also know that flat connection is uniquely determined by the image of pi1 to the gauge group. Okay, and since this guy is abelian, we know that the image will be commutative, which means actually it lives in the maximal torus. Right, okay. This tells us that we can actually do a gauge transformation so that, well, we can do a gauge transformation such that the gauge field is actually constant, and let's see. Yeah, okay. You have a constant gauge transformation such that when you constant gauge field such that when you integrate these gauge fields along this cycle or this cycle, you just get two holonomies you want. This will tell us that so let me just denote the two holonomies around this cycle and this cycle to be u and v. So e to the 2 pi I u and e to the 2 pi I v, where u and v lives in the I think they live in the dual of the Cartan subalgebra. And also, we know that syntactic form that we're supposed to be quantizing used to be this one. But now, passing down to this finite dimensional case, it becomes just delta u, delta v trace. Okay. So, we're just now quantizing this finite dimensional problem where u and v each lives in the Cartan subalgebra. And now let's just choose v. Okay, let's choose v to be the coordinate. Again, the same thing. U is the momentum. Then, again, by applying the same reasoning, we know first of all we know that u and v are defined mod k times the root lattice, because by shifting u and v, by remembering the root lattice, you're not going to change anything because it's periodic.
Are u and v spatially constant now?
Yeah. So basically.
So the integral is not needed in your.
Oh, absolutely. Thank you. Okay. So so they are defined periodically like this, and same thing. And u being the momentum of something which is defined periodically, u itself will have to satisfy this relation. Okay, this will tell me that u actually lives in 1 over k times the wave lattice. And of course, I still have a residual gauge transformation, which is the Weyl group. And there's no way I could fix away that one. So,
sorry, what is k now? I missed the k now.
K is the level here. Okay. So because you have a k here, so the momentum does not have to be integer, but integer over k. But then this is defined up to the shift of root lattice. So, okay. So we get the phase space is labeled by the phase space is 1. H, so this is labeled by the following set, 1 over k times the wave lattice divided by the Weyl group semi-direct product with the root lattice. Now this guy is the Fi Weyl group. Okay, so so this is the naive guess. In fact, the real answer is almost identical to this one, but except here we just sort of we said that we could use a gauge transformation to transform the gauge field into a constant configuration. Actually, this step is not done without punity. So,
sorry, could you just repeat the argument? Why we need to take weight lattice and divide by group and translations by root.
So the pairing between u and v, because that's the pairing between momentum and coordinate, should have been integers, but because I have a k in the this is actually the same thing here. You have a k, 1 over k here. So the momentum doesn't have to be integer, but rather just 1 over integer divided by k, because the symplectic form has got a k to it. And so the real answer actually is following.
Sorry, my question wasn't about numerator, but about denominator. Why you divide by root lattice?
Oh, this one. That's because these two guys, if you shift u or v by a root lattice, that's not going to change anything.
One is classical, the other is quantum, right? One is periodicity, which comes from the symplectic space, and the other one comes from quantization.
Yeah. This one is quantization condition. This is just because your space is defined periodically. So it's the same thing here. Here, I erased it, but you know that the momentum used to be z over k mod z. That's just because everything's defined mod z. So, okay. And anyway, the real answer is the following. There are two shifts that you suddenly would recognize. So shift of the level by the Coxeter number, and also shift of the root lattice by the Weyl vector. Okay, and we're going to see this by doing things honestly. So this is the big picture. And is there any questions? All right. So now again, following the procedure that I said, we need to find the line bundle. Is so this Chern class is this guy. Now this is an infinite dimensional problem, so I don't really want to make any guess. Let's do things according to how we are taught. And in this case, it was Quillen who provided us with the answer. The line bundle is called, this is our next subject, Quillen's determinant line bundle. So let me just introduce what is this thing. On a two-dimensional surface, you have the following operator.
Excuse me, just about the logic. Will you explain that formula, or you'll just accept it as given?
We'll derive it. When we do things correctly, you will see that.
Okay, thank you.
Okay. Then you have this complex.
So what is alpha?
Alpha is it's a connection. So it's got this index. So it's a one form.
Okay.
So basically, alpha is the A's here. Now we have this complex. And let me just call it V0 and V1. Now we can define a line element. This is a line, right? And it's defined for every alpha because okay, let me now so let me just heuristically write this guy in the following manner. Let me just strip out the kernel and co-kernel. Now, by definition, D maps this guy isomorphically onto this guy, because by definition there's no kernel here. This the image is onto, so, which means the D actually gives you a trivialization of this. It gives you an element of this line element.
So, sorry, what maps that thing to that thing?
Sorry.
You said something maps. What maps?
So the D, this D maps here.
And what is P?
P is either 0 or 1. This is the double complex.
Which is 0, 1. Oh,
right.
What is lambda 1?
Lambda 1. Oh, sorry.
Is it V1?
V1, sorry. Sorry. Any more? No. Okay. So, because D maps this guy isomorphically to this guy, so D gives you an element of what trivializes this guy. And these are going to be finite dimensional because this guy is elliptic, right? So, which means basically the strategy is that this guy is terrible, it's infinite dimensional, but for most of the bad stuff can be trivialized by just using this D, and then there's a bit of left over. You have to do it yourself. Now, let me define, so what I will do next is that I will define a Hermitian metric for this line bundle, and I will show that indeed the C1, the first Chern class associated with that metric is this guy, thereby providing us with what is the correct line bundle, the line bundle.
Can I ask for someone who doesn't speak completely this language? I mean, you're quantizing Chern-Simons. So at the end of the day, you would like to have a finite dimensional Hilbert space, I guess.
Right.
So this business you are doing now is to separate out the gauge degree of freedom in some formal way. Is that what you are about to do now?
Roughly speaking.
Because if you, as you said there, if you gauge, normally, I mean, physicist way of saying it is that you gauge fix, and you are just left with the,
right,
with the finite degrees of freedom having to do with the cycles.
So roughly speaking, this is all you want, but these guys, all they do is make this shift from K to H and this guy to...
And that's taking care of the gauge
right.
degree of freedom.
Right.
Yeah.
Okay, so, well, in fact, there's a good guess, and I'll show you why it's a good guess. Let me take the Hermitian metric just to be... let me define delta as the dagger D, then choose the Hermitian metric to be determinant, only the non-zero modes of that. And why is this a good guess? Okay, so I said that you can use...
Please, could you just repeat the logic? So you construct a line bundle given by that space?
Right, so this is a line element.
It's a line bundle over what? Over the space of...
Over the space of connections.
Over the modular space of flat connections.
And so far, I haven't said anything about a flat connection, just take it as a line bundle over connections. So this also
over
works
the
for...
space of all connections.
Right, this also works for non-flat connections.
Over the infinite dimensional space.
This is a fine
This
space.
has all the gauge
Right.
degrees of freedom in it.
Yes, so the space of this connections at affine space. So, okay. So
Why you take into account only alpha z bar, not alpha z and alpha z bar?
roughly, yeah, because I'm sort of using complex polarization. So what I will do next is that I'll take this as my, I'll take log of h, and then I will vary with respect to alpha, and then vary with respect to alpha bar. And then I'm supposed to find something like delta.
So you construct a line bundle on the space of all connections.
Right.
And
So alpha now is my connection.
and you don't quotient by the gauge transformations?
So far I'm not.
So far you don't. Okay. And then you construct metric on that line bundle?
Right.
I see.
So this is what I'm going to find, but it's
going to take some time.
okay. So let me just explain. So even though D does give you a trivialization of this bundle, but you can sort of tell that if D gets, D develops a mode which is almost singular, then the section is almost zero, and then I'm supposed to, this metric is supposed to be such that, well, when there's a mode which is not zero but almost zero, this guy goes to zero. So, which means this guy has all the correct properties that we want. And let me just, in fact, naively, you would have expected something like, you can write this guy as determinant of the, because the, well, delta is that. Naively, you would have expected that. And then this guy will be a holomorphic function, meaning it only depends on alpha, not on its conjugate. But you will find that it fails. And the failure is basically, in physics, is known as the anomaly. Okay, let's make the punch. So as usual, whenever you see this sort of delta function, a good idea is to regulate it using the Riemann-Zeke function, and that's what we shall do. Okay, I'm just, well, this is pretty much the definition of the Riemann-Zeke function, and you can see that if I take a derivative with respect to s and then set x to 0, what I'll get is exactly that, right? Well, I think what I will get, yeah, I'll get that. Is it clear? Well. And then you sum them all up, take an exponential, this converts to, and the exponential converts this to the product of all the lambdas, so it gives you the determinant. Now, next step.
Excuse me, how do you define the dagger?
Using a metric. Yes, I do need a metric.
Did you introduce metric?
I didn't.
Implicitly you have.
I should have, but I didn't say it.
But we're gonna use metric or not?
Yes, we're gonna use the metric.
Okay.
Okay, so now we have established this. S is equal to trace of delta minus S, and we could write it as remember, what we're going to do next is that we'll take derivative against S and set S to 0. And also we're going to vary with respect to both alpha and alpha bar. Now, look at this guy. Well, let me first do the variation. Delta alpha is equal to sorry. Let me vary here. So let's trace S times.
The arrow just means equality?
Yeah, but let me just vary this guy with respect to alpha. What I get is this guy. So this guy can be rewritten as then I'm going to use this identity. Okay. So remember, so this guy already vanishes as fast as s squared when I set s to 0. And then we know that eventually we'll take one derivative with respect to s and set s to 0, which means in this guy, in this factor, I only want stuff that actually blow up, because if they don't, they're going to be they will be 0 when I set s to 0. So this will help us quite a lot. Now let's do the second variation with respect to alpha bar. So as I said, I only want stuff that will blow up here. Now if alpha bar will hit this guy, it will bring down extra d, which will improve the coincidence limit, because remember you're taking a trace, which means you're taking the coincidence limit. But an extra d will improve that behavior, which will cause this guy to be finite. Not to mention that we bring down the factor of t, which will help me out as t equal to 0. So I don't want that one. And the only, which means up to the stuff that I want is going to be equal to now you already see a problem. The inverse formula should not depend on alpha bar, because D doesn't know about alpha bar. But because in order to define this inverse in infinite dimensional space, alpha bar will somehow come through anomaly. That's why you got this non-zero variation. And let's see what it is.
Is alpha bar complex conjugate of alpha?
Yes. So any other questions?
Can I ask a general question? I'm confused what exactly you're doing.
I'm trying to show this.
So you're taking a big affine space of all connections and you want to construct circular, you put a line bundle over this,
Right.
which is supposed to be trivial, right?
Yeah.
And then you're saying that, you're looking for the Euler potential for
So
this
why is it supposed to be trivial?
affine space. How do you put line bundles over affine space? Just add a line and that's it. Space of all connections is constructible.
Yes,
You can
but,
take
but
any.
usually the thing is that we quotient by Gauge transformations. Stuff with the thing
Right,
we
but
converge.
before doing quotient, he's trying, I think, to do
So
quantization
before
up,
the
and then somehow it will collapse. You will get presumably answer under the quotient.
So when we are going to quotient, are we going to quotient?
Yeah,
Because
actually,
so far the spaces are very big. If you quotient, they will be smaller, and in the end, you expect some finite dimensional spaces.
in fact, I think, in the end, the word quotient will not come out explicitly, but what we'll get is that we'll get just sort of an effective line bundle on the space of zero modes, namely constant gauge fields, and then on that space there's a metric which means it's not a trivial line bundle. I suppose the process of quotient has been encoded in there, but I
This is what I'm confused. So I know the statement about flat connections. That usual modular space of flat connection, it's a result of infinite dimensional Euler quotient, right?
okay.
So now, are you saying that if you add on the top a line bundle, then things sort of work?
Yeah.
This line bundle. So the statements eventually. You're doing this all just to argue that you will produce non-trivial line bundle of a
Right,
modular
that's-
space of flat connections. This
Right,
is
that's
the
what
upshot.
I'm going to get.
Instead of basically, this is basically gives you way to construct this line bundle instead of discussing this finite dimensional modular space.
Yeah, right.
Okay.
Sorry, I maybe should have found out about this quotient, but I tried. Yeah, okay. Anyway, it's too late to improve now. So we need to find out.
Can I ask you another question? When I try to read this thing, I got the idea is that, you are after a topological theory, and you have the gauge degrees of freedom, and normally, when you gauge fix, you have to use a metric. So, is it that the problem on some general level is to show that at the end of the day you do it properly, you get something that is topological, although in the middle you would have to put in the metric because of, and that this sort of seemingly complicated thing that you are doing is sort of aiming at that.
Spot on.
Is that a correct understanding?
Where was I? I was trying to show what is the variation of V inverse with respect to alpha bar. Let's just work out what's the kernel.
Jen? No, the people are asking questions and I speak a completely different language, so I will try to understand what is the connection. But, so are we trying to find out of this formalism this dual Coxeter number? The shifting by the Coxeter number.
Right, it will come out.
So, is it different than just looking at, you're looking at the modular, I want to do this at finite dimensional guys without looking at infinite dimensional guys. And I have this universal bundle, this modular space of bundles over your curve comes with a bundle over it, which is the universal bundle. Now take the determinant of this bundle. This is a line bundle over the modular space of all bundles. And the degree of this bundle is that Coxeter number. Is this what we're trying to compute?
You're saying a lot
Because
of words.
this is kind of, this is just the fact that the Picard group of this modular space is Z. And you're just finding...
Just say yes.
No, sorry. You're really saying a lot of words that just fly right past me. I have no idea.
It's just that this bundle, the point is you have a bundle over the modular space of all bundles. The modular space of all bundles comes with a bundle over it, which is the universal bundle. And just take the determinant of this. This is the determinant line bundle.
Are you using the determinant or not?
Sorry. And this guy has the degree that you're trying to compute, so I don't see why we have to do this infinite dimensional business.
Okay, I feel my brain's fried.
I think what he's doing, there are many ways of doing this. This is just one of the way of doing.
But is he doing this? What I'm describing sounds trivial to me, so that's why I'm trying to understand if it's the same or not.
He's suggesting another line bundle, which sounds...
Let's say yes. I don't know the argument. But
Yeah, okay.
But we still so in the end, you will get a line bundle over the modular space of flat connections.
Right, over the U and B.
The question is the degree of that line bundle going to be H? The dual Coxeter number?
No, the H will turn out to be, this term will turn out to be related to the question asked by Maxime earlier on. What happens when you deform your complex structure? This gives you sort of the metric along that direction when you deform the metric. Sorry, not to deform the metric, deform the complex structure, tau.
Raimundo said that a dual Coxeter number is the degree of what bundle? Of long
So the modular space of bundles has Picard group is Z.
Yes.
And the determinant line bundle, the determinant of the universal bundle has degree, is H bar times, so it's H, not H bar, it's H times the generator of the Picard group of the modular space. So I think this is the number that he's trying to compute.
Okay.
no, but I think the picture here is a bit, different. I don't know. It's because there is two issues. One issue, so you have to get this reduced phase space, and you have to have a symplectic structure there. Then he has to carry geometrical quantization, and he has to construct this line bundle. This is not a trivial thing. That's what he's doing. And then I think the dual Coxeter number you are talking will come later on.
And he's saying that he's giving you an alternative construction of that line bundle. He says
so perhaps this is probably in the sense that he needs this infinite dimensional thing because he wants to do geometric quantization on this infinite dimensional space. Is that correct?
I think it's just an issue of first quantize and then reduce, or first reduce and then quantize.
Yeah.
Raimundo, when you talk about model space of bundles, are you referring to holomorphic G bundles on elliptic curve?
Yes.
In holomorphic now. Here I don't think I don't think that we start with that holomorphic.
No, there's a connection between flats.
There is
flat
a
bundle
connection.
for the
Like on the right board, there is no flatness assumed and no holomorphicity assumed. It's like everything. And then the holomorphicity.
Yeah, you need to connect these two things. Yeah, correct.
Okay, so let's construct the kernel. Because I'm only interested in the limit when x is very close to y, I could just do a series extension. It's equal to So the kernel, let me call it G, X and Y. Basically, so G of X and Y times omega of Y. It's supposed to be, this has to be, okay. So, okay, the general feature is that, you see, we want this guy to hit, D hitting G should give me a delta function, but D contains a D over dz bar, which when it hits, the holomorphic variable gives you a delta function. And then the rest of the stuff is just to complete the story. But one feature I would like to point out is that if you only require this to be the delta function, then this term is not needed. But this term has to be there to maintain gauge invariance. Namely, when I apply the kernel to the gauge transform omega, I'd have better get this guy back. Right? So it has to be sort of equivariant with respect to the gauge transformation. That's why this term has to be there. And that's why this variation will pick up non-trivial term. So having done this, actually the rest of the story is rather simple. I just get. Oh, and another thing I could do is that I could replace this limit from infinite to 1, because I only want stuff that actually blow up. Then I can set this guy to equal to 1, because the difference is going to be finite. Okay, so finally I just got an integral over this guy alone, which gives me a gamma function which cancels that one. So it's just of this type, and now it's of order s, and then when I take the derivative against s, set s to 0, I just get this one back, which is what I wanted.
Again, I missed. Why did you place the upper limit of integration by 1 instead?
Because because I only want stuff that blow up. The stuff that are finite doesn't matter to me. I could do that. Right, because here you see that this guy blows up as s squared, right? Oh, sorry, this guy goes to 0 as s squared, and then I know that I will take only one derivative against s. So, which means this will vanish as s to the first power if this guy were finite. But then when I said s to 0,
you only care. Okay.
I only care about stuff that's
You only care about smallest. Yeah.
Small s and 1 over s, at least 1 over s divergent. So that's why I do all of this, and then, so in the end, I just get what I wanted, that the Chern class of the metric is indeed what I wanted. Okay. Should I stop here, or?
Well, because you were attacked by people. So.
But
Yeah.
where is the Hofstadter number?
I haven't get to that
Oh,
yet.
that's the next question.
Okay, so the next part is that
5-10 minutes.
okay, probably 5 minutes, I'll be done. So this is just showing actually this works for any of sigma 2. And then next I will just do this calculation explicitly over torus. Compute what's this guy on a torus. Again, we're on the torus, and now indeed I will. Okay. The determinants are here. I'm really doing flat connections, so I'll fix the orthogonal to be this guy and this guy, which means when I'm calculating the determinants, I'm looking. So what are the modes? Well, calculate the determinants. I just find the modes and multiply all the eigenvalues, right? So here you see that I'm really doing around flat connection because I'm fixing the gauge field to be constant, and so they're just fixed by the holonomy. Which means okay, so which means I have this following holonomy. And then the eigenmodes will be chosen.
So S is now section.
Right.
Okay. It's not this S.
Okay. So this is the eigenmodes, and the eigenvalue is quite simple. So now what we need to do is to, multiply all of these guys together and get the meaningful answer. Again, we'll be using zeta function regularization. Should I just give you the answer and call it for the day, or should I go ahead?
Go ahead for how long?
I don't know.
Well, Vasily should talk at 3 o'clock. So
Yeah.
Okay, so let me just give you the answer. Let me call U minus tau V W. So just one feature I would like to point out. I said naively I would expect this guy to be written as a something of this type, but we see that it fails because this part is really the norm squared of a holomorphic function, but this guy cannot be written as a norm squared holomorphic function. And indeed, you see that this term. So remember, this is the metric term, right? And if you calculate the you will roughly just get delta plus a few factors. Okay, so this is the determinant. Now you might wonder, why is the Cox number hasn't shown up yet? So actually what I'm doing here is that I haven't even included the algebra. So what I will do next is that, meaning tomorrow, I will put in the algebra, and then for these guys, remember they live in the dual of the they live in the dual of the they live in the dual of the Cartan subalgebra, and then when I integrate which means different roots will be charged differently under this holonomy. In particular, the guys that are in the Cartan subalgebra are not charged. Right? So when I sum all of these things up, I just get a big product of determinant of delta with different charges, and including some guys with zero charge. When I put all of these things together, what we'll find is the Weyl theta function, and with all the shifts of h and rhos and everything will be in there. Even though I regret to say that I can't tell you at which spot was the quotient took place. So I think I'll stop here and pick up tomorrow.
Any questions for John? More questions? Okay, everything is clear. Let's send John again. At 3 o'clock we have Vasily.